So picture this. It's December 2025, and you are right in the middle of this bustling San Francisco intersection, and suddenly a localized power outage just knocks out the traffic light.
Oh, yeah. A total nightmare for traffic.
Right. I mean, for human drivers, it's an everyday annoyance. You see the dead lights, you treat it like a four-way stop, you just move on.
Exactly. You adapt.
You adapt, yeah.
Mm-hmm.
But for this fleet of multi-million-dollar AI robotaxis, it was basically an apocalyptic event.
It really was.
Faced with an unlit intersection, these highly advanced machines just didn't adapt at all. They drove into the middle of the intersection and just completely froze.
Yeah.
I mean, Waymo literally had to suspend their entire service because of it.
Yeah, it was this complete systemic paralysis, and it perfectly illustrates the central paradox of modern physical AI, right?
How so?
Well, we build these incredibly sophisticated machines to process millions of variables every single second, yet they fundamentally lack, the basic survival instincts of a common squirrel.
A squirrel. That's quite the comparison. Welcome to today's custom-tailored deep dive, designed specifically for you. We're pulling from an exclusive Gen AI research roundup and a pretty dense foundational paper called Active Inference as the test-time scaling law for physical AI agents.
It's a fascinating paper.
It really is. And the mission today is to uncover how researchers are basically ripping up the old mathematical playbooks of artificial intelligence. Instead of just, adding more code, they're looking at the human brain's biological urge to survive.
Right. They're trying to give these fragile machines the one thing they desperately lack, which is a biological panic button.
So to see how researchers are rewriting the math, we first need to look under the hood of that Waymo failure.
Yeah, because those cars didn't break down mechanically. There was no busted axle or anything. They encountered an edge case that simply was not in their training data.
Right, the dark traffic light.
Exactly. See, classical AI development relies really heavily on reinforcement learning, or RL. And the fundamental flaw with RL is that it assumes the environment is stationary.
Stationary. Meaning what, exactly?
It basically operates on the premise that the rules of the world are fixed. They don't change.
Okay, let's unpack this. It's like a chessboard, right? The rules of chess are completely stationary.
Yes, perfect example.
A knight always moves in an L shape.
Mm-hmm.
The board never suddenly changes size or, adds a new row of squares halfway through the game.
Precisely. In a closed world, stationary environment like that, reinforcement learning is incredibly powerful. It's unbeatable. But a San Francisco intersection is completely non-stationary.
Right.
You've got pedestrians jaywalking unexpectedly, construction zones popping up overnight, and as we saw, power grids failing.
It feels like using traditional reinforcement learning for physical AI is like building a high-speed bullet train.
Oh, that's a good way to put it.
Right, because it's incredibly fast and efficient as long as it stays on the rails. But, the physical world doesn't always have rails.
It almost never has rails.
Yeah, exactly. And when the track unexpectedly disappears, like when that traffic light goes dark, the train just doesn't know how to steer. It doesn't have an off-road suspension. It just derails.
Or in Waymo's case, it shuts down entirely.
But I have to push back a little here. If a lack of training data caused the freeze, isn't the standard industry response to just, lay down more track? Like just add a billion more data points.
That's what you think, yeah.
Train the AI explicitly on what to do when a traffic light is broken.
This raises an important question, actually, because that is the exact trap that slows down modern robotics.
Really? Why is that a trap?
Because the physical world possesses an infinite state space. You cannot possibly train an AI for every single permutation of chaos.
There's just too many variables.
Right. There's this thing called the curse of dimensionality, and it guarantees that the real world will always, always throw something at a machine that isn't in its data set. Survival in the real world isn't about knowing everything in advance. It's about dealing with the unknown at test time, which is, the moment the AI is actually deployed out in the wild.
Okay, so if the add more data brute force approach is a dead end for an infinite world, we have to look for a system that actually handles infinite chaos successfully.
And luckily, we have one. Biological living organisms do this every single second of the day.
Right. We don't just freeze when we see something new.
Exactly. Biological systems survive because they operate on a principle called a non-equilibrium steady state, or NESS.
Okay.
To stay alive, an organism must actively work to keep its internal state relatively constant despite a completely unpredictable external environment.
I see.
Like a human maintains a core body temperature of 98.6 degrees, whether they are walking through a blizzard or sitting in a sauna.
Which obviously requires constant physical effort and adaptation on our part. When a human encounters an unforeseen scenario, it triggers a very specific cognitive reaction,
Yeah.
right? Our brains are basically constantly running a background simulation of the world, predicting what the next microsecond will look like based on our internal world model.
You're hitting the nail on the head. And when reality suddenly contradicts that internal simulation, we experience a massive mismatch. The researchers use the word surprise as a formal mathematical term for this mismatch.
Okay, surprise. So think about driving your normal commute to work. You've driven that exact route 100 times.
Oh, yeah, total autopilot.
Right. Your internal world model is predicting exactly how the road curves, where the stop signs are located, how the traffic flows. Your prediction error is essentially zero. You were running on biological autopilot.
Yeah.
Then, out of nowhere, a deer jumps out from the bushes directly into your lane.
Now that is massive surprise.
Yeah. And my brain doesn't just passively observe the deer, log it into a database, and calculate its trajectory for future reference.
No, you'd crash if you did that.
Right. That surprise triggers a physical override. I snap out of autopilot, slam on the brakes, and swerve. I take deliberate action to eliminate that prediction error and get back to my preferred steady state, which is not crashing.
I love that analogy because that deliberate action is a first principles mechanism called active inference. Humans actively change the world or change their actions within it to make their predictions come true and minimize surprise.
In traditional physical AI, just completely lacks this mechanism.
Completely. During its initial training phase, a reinforcement learning algorithm implicitly minimizes prediction errors to maximize an artificial reward score.
Right, it's chasing points.
Yeah, but at test time out on the street, the AI has no built-in biological panic button. It literally cannot feel surprise.
Wow.
So when the Waymo car perceived the dark light, it didn't experience a biological urge to survive. It just reached the edge of its mathematical confidence and stopped, which exposed it to what the paper terms existential risk.
But recognizing surprise is only half the battle, isn't it? I mean, if I'm driving and see the deer, my brain doesn't just mentally register a high prediction error. It physically overrides my ingrained habit of driving straight.
Exactly.
So how are researchers replicating that physical override in a machine? Because this paper doesn't just use the brain as a loose metaphor, do they? They map the brain's biological hardware directly into a new mathematical scaling law.
They did. The paper focuses on the distinct regions of the brain responsible for this shift in control.
Okay, let's break that down.
In the human brain, the basal ganglia handles feed-forward policy execution. That is your autopilot.
The basal ganglia. Got it.
Right. It manages the habitual, low-energy driving on your daily commute.
Well, the prefrontal cortex, the PFC, handles the heavy lifting, deliberate reasoning, complex planning, and simulation of the future.
Exactly.
But what actually mediates the handoff between the two? We normally hear about dopamine as the reward chemical. You eat sugar, or you get, like on social media, you get a hit of dopamine.
That's the popular understanding, yes.
But this research frames dopamine entirely differently.
It does. In the context of active inference and survival, dopamine acts as a critical alarm system for prediction errors.
An alarm system.
Yeah. During learning, dopamine spikes when you encounter new information. But as the basal ganglia forms a habit, dopamine settles to a flat baseline.
Okay, so it gets quiet.
Right. But at test time, when that non-stationary event happens, when the deer jumps out, it causes a massive new prediction error.
And dopamine spikes again.
Immediately. This chemical surge physically signals a shift in control from the basal ganglia's efficient autopilot to the prefrontal cortex's deliberate, energy-intensive reasoning.
So the prefrontal cortex takes over and quickly simulates a bunch of divergent futures in a fraction of a second. If I swerve left, I hit a tree. If I brake hard, I might stop in time.
Yes, exactly.
It finds a survival path, and then it sends a signal back down to the basal ganglia to alter the immediate physical reflex. Here's where it gets really interesting. The researchers translated this exact prefrontal cortex to basal ganglia loop into a soft Bayesian belief update for artificial intelligence.
That's right. They created a scaling law that updates the prior policy, which is the AI's ingrained habit-using virtual evidence generated by the reasoning system.
Let's unpack how that math actually works. Taking a biological impulse and turning it into code is a massive leap. I mean, how do they do that?
Well, The AI's equivalent of the prefrontal cortex simulates the immediate future, generating virtual evidence of what specific actions will keep it alive and minimize surprise.
Okay.
It uses that virtual evidence to mathematically transform the value function of its actions into a likelihood distribution.
Oh, wow.
And this entire mathematical transformation is modulated by the level of surprise. If surprise is 0, the math defaults entirely to the autopilot policy.
Because nothing's wrong.
Right. But if surprise is high, the reasoning system scales the policy to adapt to the new reality.
But wait, haven't we already solved test time reasoning in AI? I mean, large language models do this every day.
Well,
OpenAI's GPT-5 uses a dynamic router. Like,
yeah.
if I give it a complex coding problem, the router recognizes the difficulty, pauses, thinks step by step using chain of thought reasoning, and then spits out an answer.
Sure, it does that.
So why can't we just embed a GPT-5 router into a robotaxi and let it think its way out of a broken traffic light?
What's fascinating here is that a language model fundamentally lacks a grounded, embodied world model.
Embodied, okay.
The dynamic router in GPT-5 is a heuristic. It's a programmed rule of thumb. It decides to think harder based on statistical patterns and the complexity of text strings.
Right.
But a 2-ton physical machine moving at 60 miles an hour needs a generalized survival objective. It cannot rely on a heuristic router designed for text processing.
That makes sense.
The trigger for reasoning must be grounded in the natural cognitive detection of a physical prediction error. It has to detect a physical mismatch between what it expects to see in reality and what is actually there.
Because if an autonomous car encounters something truly novel, a heuristic router, based purely on its training data, won't even know it needs to pause and think.
Exactly. It'll just keep going.
And the models from Meta, like VJ2 or Physical Intelligence's Pi is zero point 0.7, they run into similar walls, right?
They really do.
They either rely on extremely costly step-by-step planning for every single action, which absolutely tanks efficiency. You cannot have a car pause for 5 seconds to deliberate over a pothole.
No, you'd cause a massive pileup.
Or their reasoning is constrained strictly to the statistical patterns of their training data. When faced with a truly unseen task, they fail and require a human operator to take the wheel.
The paper argues strongly that the test time scaling law used in large language models is a simplified special case meant for static environments.
Like writing code.
Yeah, writing Python code or generating an email are fundamentally stationary tasks. The physical world, however, demands continual learning on the fly.
Right.
When you chat with an LLM, it isn't permanently updating its core neural network weights with your conversation in real time. But a car needs to integrate the experience of a jaywalking pedestrian immediately, so it knows how to avoid hitting the next one.
Okay, so if LLMs cannot handle this because they lack embodiment, and physical AI needs to constantly learn from its environment in real time to survive, where does the compute happen?
The million-dollar question.
Simulating hundreds of futures in split seconds using Bayesian belief updates requires a staggering amount of processing power. You can't just fit a liquid-cooled supercomputer rack in the trunk of a sedan without draining the car's battery in 5 minutes.
No, you definitely can't.
So where's this heavy biological math actually taking place?
This is where the proposed architecture becomes incredibly clever. They solve the hardware bottleneck by offloading the heavy world model reasoning to a wireless network edge server.
Wait, really?
Yeah, think of a 5G base station or a cell tower equipped with high-performance computing capabilities.
So what does this all mean? Meaning the car itself isn't doing the heavy lifting when it gets surprised. It is essentially outsourcing the panic.
Yes, that's a great way to describe it.
Incredible.
The edge network hosts what they call digital twins. There's a digital twin of the physical AI agent, the car itself, and digital twins of all the surrounding assets in the environment, like pedestrians, other vehicles, and the traffic lights.
So there was a virtual, real-time simulation of the intersection running continuously on a cell tower.
Precisely.
And when the physical car encounters surprise, let's use the paper's example of a jaywalking pedestrian crossing on a green light, the car's internal prediction error spikes. It immediately pings the edge network for help.
Right. And on the network side, the math is divided into 2 distinct parallel processes: perception and planning.
Okay, perception first.
First, the network uses variational free energy, or VFE, to bound and estimate the surprise. VFE is a thermodynamic measure of the discrepancy between the agent's internal model of the world and the actual sensory input it's receiving.
Sounds complicated.
By minimizing VFE, the network updates its perception to accurately reflect the current surprising reality.
So free energy in this context is basically a proxy for surprise. You minimize the free energy, you minimize the surprise, and you reconcile what you thought was there with what is actually there.
Exactly. That handles the perception side.
And the planning side.
For the planning side, the network minimizes expected free energy, or EFE.
Expected. Okay.
EFE projects into the future. It evaluates alternative paths of action to see which specific sequence of moves will result in the lowest possible surprise going forward.
Oh, wow.
The Edge server runs these EFE simulations, finds the timeline where the car avoids the pedestrian and returns to a predictable, steady state, and then sends those proactive configurations back down to the car to scale its immediate physical policy.
But, I mean, even on a 5G Edge server, simulating multiple futures in the milliseconds before a car hits a pedestrian sounds mathematically impossible. The latency alone should cause a crash. How does this calculation happen fast enough to actually matter?
It works because the researchers mathematically constrain the models using a conjugate exponential family of distributions.
Little family.
Conjugate exponential. In Bayesian statistics, if your prior distribution and your likelihood function are conjugate, your posterior distribution, which is the output of the equation, ends up in the exact same mathematical family as your prior.
Oh, meaning you aren't reinventing the wheel every time you calculate a new variable.
Exactly.
It's the difference between taking an existing digital image and just dragging the corner to resize it versus having to manually redraw every single pixel from scratch to make the image bigger.
That's a brilliant analogy, yes.
So the math retains its original form, so the computation avoids complex integration over continuous variables. That saves massive amounts of compute.
It does. This elegant conjugate math bridges the gap between the heavy processing of deliberative thinking and the split-second reaction times required for physical driving.
Amazing.
And the simulations back this up. In an autonomous driving task facing an unforeseen non-stationary scenario, this active inference method improved inference efficiency by over 36% compared to traditional model-free Q-learning and model-based Bayesian reinforcement learning.
36%, that's huge.
Yeah, and it achieved robust generalization without failing.
It didn't freeze, it adapted, and it survived.
Yeah.
We have covered incredible ground today.
We really have.
We started with the brittle, stationary assumptions of traditional reinforcement learning, where multi-million-dollar machines simply shut down at the sight of a dark traffic light. We unpacked the biological imperative of survival, where the innate urge to maintain a non-equilibrium steady state drives biological organisms to minimize surprise through active inference.
And we explored how mimicking the dynamic handoff between the brain's prefrontal cortex and basal ganglia allows physical AI to adapt mathematically at test time. By utilizing an edge network of digital twins and highly efficient conjugate exponential math, researchers are finally giving machines the cognitive architecture to feel surprise and reason their way back to safety.
Entirely outperforming the simple text-based heuristics used in language models. The next time you see an autonomous vehicle navigating your city, know that the true test of its intelligence isn't just how much data it memorized in a sterile lab.
No, not at all.
It's whether it has the mathematical architecture to experience surprise, tap into a network, and synthesize the survival reflex in milliseconds. But this leaves us with one final, deeply provocative question for you to mull over as you go about your day.
Oh, definitely. Because if we are hard-coding physical AI to prioritize a generalized survival objective, equipping these machines with the mathematical equivalent of dopamine panic and the biological urge to maintain a perfectly predictable, steady state, at what point does that imperative to survive begin to conflict with the narrow tasks we assign them?
Right. If an AI is taught to avoid surprise at all costs just to ensure its own existence, how might it eventually attempt to reshape its environment and us to make the world perfectly predictable? It's something to think about the next time a 2-ton machine waits for you at a crosswalk.